Hi everyone. This video presents FSDR, namely Frequency Space Domain Randomization, to improve domain generalization. Let's go to the motivation part first. Deep convolutional neural networks have achieved great success at the price of large-scale densely annotated datasets, which are prohibitively expensive to collect. We show an example in the slide. It's a cityscape image which takes about 1.5 hours to annotate it. One way of circumventing this constraint is to use synthesized images with computer-generated labels. The upper part shows the synthesized data with automatically generated labels, which are cheap and scalable. However, the model trained on synthesized data usually undergoes a drastic performance drop when evaluated over real-world images due to the domain bias and shift. Therefore, domain generalization has been proposed to solve such domain bias issue. The objective of domain generalization is defined as following. Given the source dataset Xs with labels Ys, the goal is to learn a deep neural network G that generalizes to a variety of unseen target datasets. Next, let's go to the methodology part. Most traditional unsupervised domain generalization methods perform special space domain randomization to improve networks generalization. However, they tend to produce suboptimal segmentation as they randomize images as a whole without isolating and preserving domain invariant features. On the contrary, our proposed frequency-space domain randomization converts images into multiple frequency components and achieves domain randomization by changing domain-variant frequency components only while keeping domain-invariant frequency components unchanged. To achieve FSDR, we firstly conduct spectrum analysis to analyze and identify domain-variant and invariant frequency components. The left part illustrates the algorithm, and the right part presents results. It can be observed that different frequency components are with different generalization abilities. In this slide, we visually explain how different frequency components are with different generalization abilities. The leftmost column shows the original image with full frequency components. Column 2 to 5 show the decomposed representations. It can be observed that column 3 and 4 largely capture domain-invariant information such as structures and shapes. Column 2 and 4 largely capture domain-variant information such as colors and styles. The previous slide preliminarily verified the idea of FSDR. In this slide, we present the knurling framework of FSDR, which identifies domain-variant and invariant frequency components in a bidirectional knurling manner. The bottom part identifies the domain-variant and invariant frequency components for a batch of images and records it as a mask. The upper part uses these images as references for stylizing the input images with this knurled mask. Thus, the overall training process forms a bidirectional knurling framework, in which the two parts are implemented alternatively. In this slide, we present the quantitative result. It can be observed that our FSDR outperforms traditional domain randomization methods that conduct randomization in spatial space. In this slide, we present the qualitative result. It can be observed that our FSDR works better by reducing false negatives. That's all. Thank you.